Imagine building a railway so vast that you could circle the earth using nothing but its tracks, connecting hundreds of cities, crossing mountains, rivers, deserts, and some of the world's busiest megacities. Most countries spent decades planning high-speed rail. China built the largest network on Earth.
Every civilization leaves a mark. These are the echoes of power.
High-speed rail has transformed transportation across the world, but nowhere has that transformation happened faster, or on a larger scale, than in China. In just a few decades, the country constructed tens of thousands of kilometers of dedicated high-speed railway. Today, passengers can travel between distant cities at speeds exceeding 300 kilometers per hour. Journeys that once required an entire day can now take only a few hours. But this story isn't simply about fast trains. It's about one of the largest infrastructure programs in modern history. Thousands of bridges, thousands of kilometers of tunnels, millions of concrete sleepers, advanced signaling systems, electrified rail corridors, and engineering solutions designed to operate safely across mountains, floodplains, seismic zones, and densely populated cities. Building a single high-speed railway is difficult. Building an entire national network is something else entirely. The greatest challenge wasn't making one train go faster. It was creating an infrastructure system capable of moving millions of passengers every day with extraordinary precision. At first glance, expanding existing railways seemed like the obvious solution. Simply add more tracks, run faster trains, increase capacity. But engineers quickly realized the problem was far more complex. Traditional railways were already carrying a mixture of passenger trains, freight trains, and regional services. Each travels at very different speeds. A freight train may move at less than 100 kilometers per hour. A conventional passenger train travels considerably faster. A high-speed train, however, operates at more than 300 kilometers per hour. Trying to run all of them on the same tracks creates a serious engineering problem. The faster train constantly catches the slower one. Schedules become increasingly difficult to manage. Small delays spread rapidly across the network. Overall capacity actually decreases. Instead of improving the existing system, Chinese engineers chose a far more ambitious approach. Build an entirely separate railway network designed exclusively for high-speed operation. This decision changed every aspect of the project. The tracks had to be straighter. Curves needed much larger turning radii. Gradients had to remain gentle enough for trains traveling at aircraft-like ground speeds. Even tiny imperfections in track alignment could affect passenger comfort and long-term safety. Entirely new stations were designed. Dedicated maintenance facilities were constructed. Advanced electrical systems supplied continuous power across thousands of kilometers. Most importantly, engineers were no longer building individual railways. They were designing a national transportation system where every line would eventually connect with another. But creating that network introduced an even greater challenge. How do you build high-speed rail across a country with mountains, rivers, deserts, earthquakes, and some of the world's busiest cities without slowing the trains down? When people imagine a railway, they picture tracks resting directly on the ground. But for China's high-speed rail network, that approach wasn't good enough. At speeds above 300 kilometers per hour, even tiny ground movements can affect ride quality and long-term maintenance. Soft soil settles, floodplains shift, road crossings interrupt traffic. Every obstacle forces engineers to reduce speed. The solution was surprisingly simple. Lift the railway above the landscape. Today, thousands of kilometers of China's high-speed network run on elevated viaducts. Some cross rivers, others pass over highways, farmland, entire cities, or wide floodplains where seasonal water levels constantly change. Building on viaducts solved several engineering problems at once. Road traffic could continue underneath. Floodwater flowed naturally during heavy rains. Land acquisition was reduced. Most importantly, the railway followed a straighter, more stable path. Each concrete span was engineered to distribute enormous dynamic loads generated by trains traveling faster than commercial aircraft during takeoff. Expansion joints accommodate temperature changes. Bearings absorb structural movement. Precision surveying during construction ensured neighboring bridge sections aligned within extremely small tolerances. Because at 350 kilometers per hour, even the smallest construction error becomes magnified. But bridges alone couldn't keep the railway straight. Eventually, the network reached one obstacle engineers couldn't simply cross above: mountains. High-speed trains have one major weakness: they don't like sharp turns. Unlike highways, railways cannot simply weave around mountains. Every curve forces trains to slow down, and slowing down defeats the entire purpose of high-speed rail. Chinese engineers made a different choice. Instead of routing tracks around mountains, they went through them. Across western and central China, hundreds of tunnels were excavated through some of the country's most challenging terrain. Each tunnel demanded extensive geological investigation before excavation even began. Engineers studied rock strength, fault zones, groundwater conditions, and long-term stability. Different ground conditions required different excavation techniques. In strong rock, tunnel boring machines could maintain steady progress. Elsewhere, the drill and blast method remained more effective, but excavation was only the beginning. High-speed tunnels must maintain exceptionally smooth geometry. Ventilation systems manage pressure changes as trains enter at hundreds of kilometers per hour. Drainage networks prevent groundwater from damaging the structure. Emergency passages improve operational safety throughout longer tunnels. Every tunnel became far more than a hole through a mountain. It became a precisely engineered environment, allowing trains to maintain speed while crossing terrain that once acted as a natural barrier. Yet mountains weren't the only challenge. Even after tunnels and bridges were complete, engineers still faced another invisible enemy: vibration. Speed changes everything. At conventional railway speeds, small imperfections in the track may go almost unnoticed. At 350 kilometers per hour, those same imperfections create powerful vibrations. Over time, vibration increases maintenance costs, reduces passenger comfort, accelerates component wear, and places additional stress on both the train and the infrastructure. To overcome this, Chinese engineers relied heavily on ballastless track. Unlike traditional railways that rest on crushed stone, many high-speed lines use reinforced concrete track slabs anchored with extraordinary precision. This creates a much more stable foundation. Track geometry remains consistent for longer periods. Maintenance requirements decrease, and trains experience smoother operation even at extremely high speeds. Advanced inspection trains continuously scan the network using lasers, high-speed cameras, and precision measuring equipment. They can detect tiny changes in rail alignment long before they become operational concerns. Maintenance crews then correct these issues during scheduled inspection windows, ensuring the railway continues meeting its strict engineering standards. The result is a transportation system where trains routinely travel at extraordinary speeds, while passengers often experience a ride smoother than many conventional railways operating at half the speed. But building the tracks was only part of the challenge. The real engineering miracle was making thousands of trains move across this enormous network without colliding or even slowing each other down. Building thousands of kilometers of railway was an enormous achievement. But infrastructure alone doesn't move passengers. Operations do. Imagine hundreds of high-speed trains traveling simultaneously, often at speeds exceeding 300 kilometers per hour. Some stop frequently. Others operate as express services. Many share major junctions before separating onto different corridors. Without precise coordination, even a small delay could spread across the entire network. To prevent this, engineers designed one of the world's most advanced railway control systems. Every train continuously exchanges information with the railway network. Its speed, location, direction, and operating status are constantly monitored. Instead of relying solely on traditional trackside signals, high-speed lines use digital communication systems that transmit movement authority directly to the train. Onboard computers constantly calculate safe operating speeds. If a driver exceeds those limits, automatic train protection immediately intervenes. Braking can occur automatically without human input. This dramatically reduces the possibility of human error while allowing trains to safely operate much closer together than conventional railways. Traffic control centers oversee thousands of kilometers of railway in real time. Operators don't simply react to problems. They predict them. Train spacing is continuously optimized. Schedules are adjusted. Conflicts are resolved before passengers ever notice. At these speeds, railway operation becomes less about driving trains and more about managing information. But even perfect scheduling cannot overcome one unavoidable force: electricity. Without power, the entire network stops. A high-speed train consumes an enormous amount of energy, accelerating hundreds of tons to over 300 kilometers per hour requires continuous electrical power. Now imagine hundreds of those trains operating simultaneously across thousands of kilometers. Delivering electricity at that scale became a megaproject of its own. Instead of diesel locomotives, China's high-speed network relies almost entirely on electrification. Overhead catenary wires supply high-voltage electricity directly to each train through a pantograph mounted on the roof. But supplying electricity isn't as simple as stretching wires above the tracks. Voltage must remain remarkably stable, even during peak travel periods. Substations positioned along the railway convert electricity from the national grid into the precise voltage required for railway operation. These facilities work together like stepping stones, continuously feeding power into the network. If demand suddenly increases, additional sections automatically balance the electrical load. Protection systems constantly monitor for faults. If a damaged section is detected, power can be isolated almost instantly while neighboring sections continue operating. Modern high-speed trains also improve efficiency through regenerative braking. During deceleration, electric traction motors temporarily become generators. Instead of wasting kinetic energy as heat, part of that energy is returned to the electrical network where it can help power other trains. It's a remarkable example of engineering efficiency, but supplying electricity is only half the challenge. The trains themselves must also survive one of the harshest operating environments in transportation: thousands of kilometers. Every single day, building a railway is difficult. Maintaining one this large is an entirely different engineering challenge. Every day, thousands of trains place enormous dynamic loads on rails, bridges, switches, power systems, and signaling equipment. Tiny defects can grow quickly if left unnoticed. That's why maintenance begins long before something breaks. Specialized inspection trains regularly travel across the network at high speed. Using lasers, ultrasonic sensors, thermal imaging cameras, and precision measurement equipment, they inspect rails, overhead wires, bridges, and tunnels while collecting millions of data points. Artificial intelligence increasingly assists engineers by identifying patterns that may indicate future failures. Instead of replacing components after they wear out, maintenance can be scheduled before performance begins to decline. This approach is known as predictive maintenance. It reduces service disruptions, improves passenger safety, and extends the lifespan of critical infrastructure. Many inspections also occur overnight. When passenger traffic is lower, teams work within carefully planned maintenance windows. Every minute is coordinated, because by sunrise, the railway must be ready to carry millions of passengers once again. Keeping the world's largest high-speed rail network operating isn't a single engineering achievement. It's a continuous process repeated every day. And after mastering construction, operations, power, and maintenance, one final question remains. Has China's high-speed rail network changed the future of transportation? Or is this engineering model impossible for other countries to replicate? China's high-speed rail network didn't become the world's largest simply because of faster trains. It succeeded because engineers designed an entire transportation ecosystem. The tracks, the trains, the stations, the electrical grid, the signaling systems, and the maintenance infrastructure were all developed as one integrated network. Could another country build the same thing? Technically, yes. Practically, it's far more complicated. Every country faces different engineering challenges. Some have mountain ranges, others have deserts, earthquake zones, dense urban centers, or vast areas with relatively small populations. A high-speed railway only works efficiently when it connects cities capable of generating enough passenger demand to justify the investment. Engineers must also consider land acquisition. Long, straight alignments often require crossing farms, rivers, highways, and existing neighborhoods. Every bridge, every tunnel, every station adds complexity to the project. That's why many countries begin with shorter high-speed corridors before expanding into larger national networks. China's experience demonstrates that successful railway engineering isn't just about building tracks. It's about long-term planning. Each new corridor strengthens the entire network rather than operating as an isolated line. The result is a transportation system where every additional railway increases the value of all the others. And that systems thinking may be China's greatest engineering achievement. But railway technology continues evolving. The next generation of high-speed transportation could look very different from today's network. Building the world's largest high-speed rail network wasn't the finish line. It became the foundation for future innovation. Engineers are now developing smarter infrastructure capable of monitoring itself continuously. Fiber optic sensors embedded along railway corridors can detect tiny structural movements before they become maintenance problems. Artificial intelligence analyzes enormous volumes of operational data, helping engineers optimize train schedules, predict equipment failures, and improve energy efficiency. Digital twins, virtual models of physical railway systems, allow engineers to simulate everything from extreme weather events to future passenger demand without disrupting real-world operations. Future trains are also becoming lighter, more aerodynamic, and more energy efficient. Advanced materials reduce weight while maintaining structural strength. Improved traction systems increase efficiency during acceleration. Regenerative braking continues recovering energy that would otherwise be lost. Meanwhile, next-generation signaling systems may safely reduce train spacing even further, increasing network capacity without building additional tracks. The future of railway engineering isn't simply about making trains faster. It's about making entire transportation systems smarter. Because in modern infrastructure, information travels just as fast as the trains themselves. And perhaps that's the biggest lesson this network offers. The world's largest railway wasn't built solely with steel and concrete. It was built with engineering systems designed to work together as one. Every day, millions of passengers step onto high-speed trains across China. For them, it's simply another journey, a commute, a business trip, a visit home. Few stop to think about what makes that journey possible. Thousands of kilometers of precisely aligned track, bridges stretching across valleys and rivers, tunnels carved through mountains, power systems delivering electricity every second, digital control centers coordinating thousands of train movements with remarkable precision. This isn't just a railway. It's one of the largest interconnected engineering systems ever constructed. The true achievement isn't that trains travel at more than 300 kilometers per hour. It's that they do so safely, reliably, and every single day across a network spanning an entire nation. China's high-speed rail transformed how engineers think about transportation infrastructure. It proved that railways are no longer isolated lines connecting two cities. They can become the backbone of a country's economy, a catalyst for regional development, and a demonstration of what's possible when engineering is planned on a national scale. The future of transportation won't be defined by speed alone. It will be defined by how intelligently infrastructure connects people, cities, and opportunities. This is Echoes of Power. If you enjoyed exploring the engineering behind the world's largest high-speed rail network, subscribe for more documentaries uncovering the megaprojects, innovations, and engineering breakthroughs shaping the future of our world.